In the year 1828, a man named Edward Quinn, an amateur cartographer with a passion for history, completed a work unlike any before it. His historical atlas was not just a map of places, it was a map of time, of expanding awareness. Its pages did not merely trace borders or name empires. They depicted knowledge as a trembling flame, gradually pushing away the clouds of ignorance that had long obscured the world. Through the murk, continents emerged. Civilizations stepped into the light. From the cradle of Mesopotamia to the far corners of the known Earth, Quinn's atlas told a story, not of land, but of human understanding. As one turns the pages, time unfolds. The Bible, the Roman Empire, the voyages of discovery, all appear as bursts of clarity in a world once drenched in shadow. With each step forward, more of the earth becomes visible. By the 19th century, the clouds have parted entirely. Every continent has been charted, every ocean named. But the story carries a subtle bias. This light, this knowledge, is European in origin and perspective. Had Quinn lived in China, or India, or the ancient Americas, the fog would have parted differently. Every culture carries its own light, its own beginning, its own myths, and its own darkness. And that darkness is not merely geographic. Every pursuit of knowledge begins in a kind of fog, a haze of mystery, of partial understanding. That haze does not just surround distant lands, it surrounds the universe itself. Just as the Earth was once hidden behind clouds of uncertainty, so too was the cosmos. For most of human history, the night sky was a canvas of unanswerable questions. What are stars? What lies beyond them? Is there an edge to existence, or does it stretch on forever? These questions loomed, barely visible through the mist of unknowing. But something began to shift. As our maps of Earth reached their edges, our curiosity turned upward. With telescopes aimed at the heavens, we pierced through the night. We discovered that stars are suns, that galaxies are countless in number, and that the universe had a beginning. In a way, we started creating a new kind of atlas, one not drawn on parchment, but on light, data, and time. A cosmic atlas, born not from sea voyages, but from equations and observations. And just like Quinn's vision, it begins with a flicker of insight, and it continues to burn away the fog of the unknown. For most of human history, the universe was what we could see with the naked eye. The night sky was familiar, yet deeply mysterious, a ceiling of stars, seemingly fixed, sprinkled across the heavens. Ancient peoples charted these patterns, naming constellations, telling stories of gods and heroes woven into the stars. The Greeks believed the heavens moved in perfect circles. The Chinese, Babylonians, Mayans, all kept records of the sky with remarkable precision. But even with such care, the universe remained static, timeless, and complete. It was a dome, not a vast ocean. Everything began to change in the early 17th century. With a simple instrument, two lenses placed in a wooden tube, Galileo Galilei turned his gaze to the heavens and saw what no one had ever seen before. The moon had mountains. Jupiter had moons. The Milky Way was not a ghostly smear, but a river of countless stars. Galileo's telescope shattered the illusion of a perfect, changeless sky. It revealed motion, imperfection, and vastness. But still, our vision was limited. For the next 3 centuries, astronomers refined their tools, searching deeper, yet still unsure of just how big the universe truly was. By the early 20th century, the sky remained filled with puzzling objects, dim, spiral-shaped smudges of light scattered among the stars. Astronomers called them nebulae, Latin for clouds, and no one could say what they truly were. Were they part of the Milky Way, or were they something beyond? 2 astronomers, Harlow Shapley and Heber Curtis, stood at the center of this debate. In April of 1920, they took the stage at the Smithsonian in Washington, D.C., for what would later be called the Great Debate. The question was simple, yet profound. How large is the universe? Shapley believed that the Milky Way was the entire universe. Everything, every star, every nebula, every object was contained within our galaxy. He acknowledged the spiral nebulae, but insisted they were just clouds inside the Milky Way itself. Curtis, on the other hand, argued the opposite. He believed that the nebulae were not part of our galaxy at all. They were island universes, entire galaxies in their own right, separated by unimaginable distances, each filled with billions of stars. That night, no clear winner emerged. The question remained unsettled. But not for long. On the other side of the country, a young astronomer named Edwin Hubble had just begun his work at Mount Wilson Observatory in California. With the powerful 100-inch Hooker telescope, the largest in the world at the time, Hubble focused on one of the spiral nebulae, Andromeda. He examined its light carefully, searching for a special kind of star known as a Cepheid variable. These stars pulse with a predictable rhythm, and that rhythm can reveal their true brightness. By comparing how bright they appear with how bright they truly are, Hubble could determine their distance. And when he did, the result was astonishing. The Cepheid variables in Andromeda were far too faint to exist within the Milky Way. They were much farther away, hundreds of thousands of light-years beyond our galaxy's edge. Andromeda was not a cloud. It was not a nearby object. It was an entire galaxy, just as Curtis had proposed. In 1924, Hubble sent a letter to Shapley announcing his discovery. Shapley's response was as poetic as it was painful. He said, "Here is the letter that destroyed my universe." The debate was over. The fog had lifted, and the cosmos had become unimaginably vast. The universe, vast as it is not infinite in what we can observe. There exists a cosmic horizon, a boundary defined not by geography, but by time. It marks the edge of what we can see, the limit of how far light has had time to travel since the birth of the universe. No matter how powerful our telescopes become, we are confined within this horizon. We call it the observable universe, a sphere centered on Earth that stretches roughly 93 billion light-years in diameter. Beyond that, we are blind, not by lack of will, but by the laws of physics. The reason for this limit lies in the age of the universe itself. Light travels at a finite speed, and the universe has existed for a finite amount of time, around 13.8 billion years. That means we can only see as far as light has been able to travel since the beginning. However, because space itself has been expanding all the while, the actual distance to the most distant objects we can observe is much greater than 13 billion light-years. This strange but measurable truth is a consequence of cosmic inflation and the dynamic nature of space-time. At the edge of this observable boundary lies a faint signal, the oldest light we can detect. It is called the cosmic microwave background, or CMB, a soft, uniform glow left over from a time just 380,000 years after the Big Bang. Before that, the universe was a hot, opaque plasma where light could not travel freely. But as the cosmos cooled, atoms formed, and light was suddenly released in all directions. This ancient light still bathes the universe today, stretched into microwave frequencies by the expansion of space itself. Discovered by accident in the year 1964, the CMB became one of the most important pieces of evidence for the Big Bang. It is not just the boundary of visibility, it is the edge of our cosmic map. We cannot see beyond it with light, no matter how advanced our technology becomes. It forms a kind of horizon, not unlike the one we see at sea, an illusion of finality, though we know more lies beyond. We are trapped inside a cosmic bubble, our knowledge limited by time, distance, and the unyielding speed of light. But what lies beyond that horizon? If we could somehow reach past the CMB, what would we find? The answer, most physicists believe, is more universe, perhaps infinitely more. There is no reason to believe that the universe ends where our observations stop. Instead, it likely continues on, with stars, galaxies, and entire structures of matter, stretching out far beyond what we can ever hope to see. The only thing separating us from them is the time it takes their light to reach us, a delay that may never be overcome. In that sense, our universe is both complete and incomplete. Complete because we can chart everything within our cosmic bubble. Incomplete because we know that this bubble is not all there is. Our observations are limited to the visible, but our imagination, our equations, and our models hint at a reality far greater. The observable universe is not the end of the story, it is merely the beginning. Just as ancient maps once marked the edge of the known world with warnings of sea monsters, we now stand at a modern boundary, one drawn not in ink, but in starlight. For centuries, our understanding of the universe has grown outward, from a flat Earth beneath a dome of stars, to a spinning globe circling the sun, to a galaxy adrift in a cosmic sea. Each step outward has expanded not only the size of our known reality, but also our sense of wonder. And yet, with every question answered, more profound mysteries remain. One of the deepest among them is this: why does our universe have the particular laws of physics that it does? Why is gravity just strong enough to form stars, but not so strong that the universe collapses upon itself? These questions strike at the heart of existence. If the strength of gravity, the mass of the electron, or the balance between forces were even slightly different, life as we know it would not be possible. Stars might never ignite, atoms might not form. The universe would be dark, sterile, and lifeless. And yet, here we are, living in a cosmos that seems perfectly tuned for complexity. This has led many physicists and philosophers to consider an audacious idea. Perhaps our universe is just one of many. Perhaps it is one drop in a vast cosmic ocean. This is the idea of the multiverse. At first glance, it may seem like science fiction, or even fantasy. But the multiverse is not a single theory. It is a collection of possibilities, some born from observations, others from the implications of well-tested physics. It arises not from wild speculation, but from following existing theories to their logical extremes. Quantum mechanics, cosmic inflation, and string theory all suggest that our universe might not be alone, that what we think of as everything may in fact be only a part. The concept of a multiverse allows us to reframe the fine-tuning problem. If there are countless universes, each with different physical laws, then perhaps it is no surprise that one of them happens to support life. We do not live in this universe because it was made for us. We live here because it is one of the few where life is even possible. In this way, the multiverse does not explain why our universe is special. It suggests that it is not special at all. It is merely one realization among infinite others. Over the next chapters, we will explore 4 levels of the multiverse, each more mind-bending than the last. From distant cosmic regions beyond our horizon, to branching realities within quantum mechanics, to alien universes governed by different laws, and finally, to a realm where all that exists is mathematics itself. These are not merely stories. They are testaments to how far our understanding has come, and how much further it might yet go. Welcome to the edge of everything. Welcome to the multiverse. Imagine standing at the edge of the observable universe, staring into the darkness beyond. What lies out there, past the reach of our most powerful telescopes? According to modern cosmology, the answer may be simple: more universe. The idea behind the Level 1 multiverse is not rooted in fantasy, but in the geometry of space itself. If the cosmos is infinite in extent, and the laws of physics remain consistent throughout, then our observable patch is just one region in a much larger whole. There are no hard edges, no cosmic walls, just space continuing endlessly, filled with stars, galaxies, and perhaps other Earths, other yous. In a universe without boundaries, the possibilities are not just vast, they are infinite. What we call the observable universe is not the entire universe. It is simply the region from which light has had time to reach us since the beginning of cosmic history. It is a cosmic bubble centered on Earth, stretching some 93 billion light-years across, not because the universe is that old, but because space itself has been expanding over time. And beyond this bubble, we believe there is more, much more. The universe may continue on forever, far beyond what we can see or measure. And if space is indeed infinite, then there is no edge, no final frontier where existence comes to an end. Instead, our observable universe becomes just one patch, one pocket, in a vast and possibly unending cosmic quilt. Each region beyond our horizon may look very much like our own, governed by the same physical laws, filled with stars and galaxies. But because the speed of light is finite, we can never exchange signals with them. They are causally disconnected, permanently out of reach. No matter how fast we travel or how long we wait, their light will never touch us. To us, they are invisible, but that does not mean they are not there. In fact, if space is truly infinite, then there may be an uncountable number of such regions, each a universe in its own right. We live in one of these cosmic bubbles, but we are not alone. Modern cosmology rests on a powerful assumption that the laws of physics are the same everywhere. Gravity pulls, atoms bind, and light travels at the same speed, no matter where you are in the cosmos. This is known as the principle of uniformity, and it leads to a staggering conclusion. In an infinite universe governed by consistent laws, every possible arrangement of atoms will eventually occur, somewhere. That means, given enough space, there will be regions that look almost exactly like Earth. And far beyond the most distant galaxies, there may exist a planet that mirrors ours completely. A world with the same mountains, oceans, and even people. Not as fiction, but as a statistical inevitability written into the fabric of infinite space. In an infinite universe, where the laws of physics do not change, everything that can happen must happen, somewhere. That includes you, not just similar people, but exact copies. Somewhere, unimaginably far away, another version of you is living your life. They have the same memories, the same thoughts, the same hopes and fears. Perhaps, at this very moment, they are watching this very same video, thinking the same thoughts you are thinking now. It may sound impossible, but mathematically, it is not. With only a finite number of ways atoms can be arranged in a given volume, those arrangements must begin to repeat if space continues forever. And just like repeating wallpaper patterns, eventually the cosmos runs out of new combinations. These doppelgangers are not science fiction. They are a logical consequence of infinity. They live in galaxies so distant that their light will never reach us. But they are out there, written into the fabric of space, like echoes in an endless hall of mirrors. According to physicist Max Tegmark, if the universe is truly infinite, then the distance to the nearest identical copy of you is roughly 10 to the power of 118 meters away. That number is so large it defies imagination, far beyond the scale of any galaxy, any cluster, or even the entire observable universe. And yet, in the mathematics of infinity, such distances are not only possible, they are expected. Somewhere out there, unimaginably far across space, your cosmic twin lives, unaware of your existence. You will never meet them. No message can travel that far. No light can ever bridge the gap. They are causally disconnected, forever beyond reach. But their existence is written into the logic of an infinite universe, where the improbable becomes inevitable and the unimaginable becomes real. If the universe is infinite and the laws of physics are the same everywhere, then everything we know, our world, our lives, even our very thoughts, may be only one version among countless others. This raises a profound question. Are we truly unique? Or are we just one expression in a vast sea of possibilities, playing out over and over again in the endless expanse of space? It is a humbling idea. For much of history, we believed ourselves to be at the center of everything. First the Earth, then the Sun, then the galaxy. And now, we may find that even our universe is not central, not final, not singular. In the Level 1 multiverse, we are part of something far larger, an infinite patchwork of realities that mirror and diverge from our own. But this is not a reason to despair. On the contrary, it is a reminder that the cosmos is far more mysterious and beautiful than we imagined. That even in a universe where we are not alone, not even in our own identity, our experiences still matter, because they are part of this vast, unfolding story. And yet, the Level 1 multiverse is only the beginning. For if space itself can be infinite, what about the laws that govern it? Could they too vary from place to place? What if, beyond the limits of our cosmic bubble, lie other universes, not just far away, but fundamentally different? Let us step forward into the next possibility, the multiverse born from eternal inflation. Level 2 awaits. In the Level 1 multiverse, the cosmos stretches out endlessly, repeating, echoing, recombining. But what if there is more? What if the universe does not just repeat in space, but varies in its very nature? What if the laws of physics themselves can change? This brings us to a deeper idea, Level 2. In this multiverse, each universe is like a bubble, born from the early moments of cosmic inflation, and within each bubble, the rules may be entirely different. One universe may have no stars, another no chemistry. Ours, by chance or by necessity, is one where life is possible. Shortly after the Big Bang, the universe did something extraordinary. In a fraction of a second, it expanded at a speed that defied all common sense. This sudden growth, known as cosmic inflation, was not like ordinary expansion. It was faster than the speed of light. Space itself stretched, smoothing out the cosmos, flattening any curves, and scattering matter evenly across the void. Without inflation, the universe we observe today would be chaotic, uneven, and unrecognizable. But what caused this inflation? Physicists believe it was driven by a mysterious energy field called the inflaton. This field, unlike anything we know today, filled space with an immense energy density. As it decayed, it released that energy in a colossal burst, triggering the expansion of space itself. The inflaton is not a particle or a substance. It is a property of space, a kind of hidden engine embedded in the earliest moments of existence. Yet, inflation, for all its elegance, came with a puzzle. In theory, inflation should have ended uniformly everywhere, like turning off a switch. But the equations told a different story. They suggested that inflation does not stop all at once. In some regions, it ends quickly, giving birth to a universe like ours. But in others, inflation continues, eternally expanding, pushing those regions farther and farther away. These growing patches never settle. They keep inflating, forever birthing new regions where inflation randomly ends and new universes emerge. This strange idea, eternal inflation, leads us directly into the heart of the Level 2 multiverse. Each universe forms like a bubble in a boiling pot, a local pause in an otherwise endless expansion. And each bubble may be governed by different physical conditions, different constants, perhaps even different dimensions. In trying to understand why our universe looks the way it does, we may have uncovered a reality in which countless other universes are constantly being born, just beyond reach. In the vast landscape of eternal inflation, something remarkable happens. Inflation does not end everywhere at once. Instead, it stops in isolated pockets, bubbles, while the space around them continues to expand. Each of these bubbles becomes a universe, disconnected from the others, floating in a sea of still inflating space. Our universe is just one such bubble, a single sphere of stability in an eternally growing multiverse. But here is where the story becomes truly strange. When inflation ends inside a bubble, the properties of that universe are not guaranteed to match our own. The fundamental constants, such as the strength of gravity, the mass of the electron, or the rate at which nuclear reactions occur, may be different. The number of spatial dimensions could vary. Even the underlying structure of matter might be unrecognizable. In some bubbles, the forces of nature may be so imbalanced that no atoms can form. In others, gravity might be too weak for stars to ignite or too strong for galaxies to hold together. These universes are sterile, cold, and empty, cosmic stillbirths in a sea of possibility. But every so often, by chance, a bubble forms where everything aligns just right. The forces balance, stars light up, chemistry becomes possible, and life, in all its fragile complexity, can emerge. Our universe may be one of these rare, fortunate bubbles, not because it was designed, but because in a multiverse where all possibilities exist, even the improbable will eventually appear. In that view, we are not the center of the cosmos. We are one statistical outcome in an infinite experiment, a spark that caught in the right conditions, while countless others faded without a trace. As we peer more deeply into the workings of our universe, one feature stands out with unsettling clarity. Everything appears finely tuned for life. The forces that govern nature are balanced with exquisite precision. If gravity were even slightly stronger or weaker, stars might not form or would burn too quickly. If the electromagnetic force were different, atoms could not bind. If the strong nuclear force were just a bit off, the carbon essential to our bodies would never have formed inside stars. This apparent fine-tuning is one of the great puzzles of modern physics. Why should the universe, among all possible configurations, happen to possess the rare combination of conditions that allow life to exist? It seems too precise, too convenient, almost as if it were made for us. One way to answer this question does not require invoking design or intention, but rather probability. In an eternal inflationary multiverse, there are countless universes, each a bubble with different physical laws. Most of these universes are sterile, incapable of producing complexity, let alone life. But in a small subset, the conditions are just right. Stars shine, planets form, molecules dance, and life has a chance to awaken and ask why it is here. This is where the anthropic principle comes into play. It simply states, we observe the universe to be suitable for life because if it were not, we would not be here to observe it. Our very presence biases our perspective. Out of all the possible universes, we find ourselves in one of the few where life is possible, not because it was destined, but because it was the only place where life could ever ask the question. In the grand lottery of the cosmos, we inhabit one of the winning tickets. Not all Level 2 multiverses arise from eternal inflation. Some emerge from entirely different visions of reality, ones that rewrite the very rhythm of the cosmos. One such idea is the cyclic universe. Instead of a single beginning in a fiery Big Bang, the universe may live through endless cycles of expansion, contraction, and rebirth. Each universe gives way to the next, like a cosmic heartbeat pulsing through eternity. This notion is ancient, echoing traditions from Hindu cosmology to Stoic philosophy. And yet, Modern physics once gave it serious thought. But there is a problem: entropy. With each cycle, disorder increases. So how, after an infinite number of past cycles, do we find ourselves in a universe so rich with structure and life? Another bold idea comes from physicist Lee Smolin, who proposed that every black hole may be a portal to a new universe. In this view, our cosmos gives birth to new universes whenever stars collapse into black holes. Each of these baby universes inherits the basic physics of its parent, but may vary slightly, like genetic mutations in biology. Some are sterile, unable to form stars, but others, like ours, thrive. Over time, star-forming universes become more common. This cosmic natural selection suggests a multiverse that evolves, generation by generation. And then, there is the Phoenix universe, envisioned by Paul Steinhardt and Neil Turok. Drawing on the mathematics of string theory, they imagine that our universe exists on a vast cosmic membrane, a brain, floating in higher dimensional space. Every few trillion years, it collides with another brain, releasing a storm of energy and giving birth to a new cosmos. Each collision wipes the slate clean, resets entropy, and sparks a fresh Big Bang. Like the mythical phoenix, the universe dies in fire, only to rise again from the ashes. The Level 2 multiverse expands our imagination beyond measure. Here, the variety of universes is not just spatial, it is fundamental. Each bubble may follow different laws, host unfamiliar forces, or unfold in unexpected dimensions. Ours is simply one of many, balanced delicately enough to permit life. But now, we must ask a deeper question. If space can split into bubbles with varying physics, what about reality itself? What if the universe divides not only through cosmic inflation, but through quantum decision? What if every time a particle chooses a path, the universe splits, creating not one future, but all possible futures? Welcome to the next frontier. Welcome to the Level 3 multiverse, where reality is not singular, but branching endlessly with every quantum choice. At the heart of modern physics lies a strange truth. The universe, at its most fundamental level, behaves like both a wave and a particle. Light can interfere like ripples on a pond, yet hit a screen as single, discrete photons. Electrons can be smeared across space like a mist of probability until we measure them. Then they appear as a single point. One moment, uncertainty. The next, clarity. This bizarre duality is the foundation of quantum mechanics, and with it comes one of science's most perplexing questions. What actually happens when we observe something? According to the standard interpretation, known as the Copenhagen interpretation, the act of observation collapses the wave function. That is, the spread-out cloud of possibilities suddenly snaps into a single outcome. Before we look, the electron is everywhere. After we look, it is somewhere. But what counts as an observation? Does it require a human mind? A machine? A photon bouncing off a surface? This seemingly simple question has troubled physicists for nearly a century, because nowhere in the mathematics of quantum theory is this collapse actually described. It is not in the equations. It is added afterward, a rule tacked onto an otherwise elegant system. Some call it pragmatic, others call it embarrassing, and yet we still teach it, use it, rely on it, because it works. But for some, this ad hoc solution is not enough. If the laws of physics are truly universal, then we should not need a separate rule for measurement. Perhaps the wave function never collapses at all. Perhaps reality, at its core, never makes a choice. Instead, it follows every path, every possibility, at once. And if that is true, then we must prepare ourselves for an even stranger idea, that every quantum event creates a new universe. In the year 1957, a young physicist named Hugh Everett proposed a radical solution to quantum theory's most nagging puzzle. What if the wave function never collapses at all? What if, instead of choosing one outcome, the universe allows every possibility to happen, in parallel? Everett's idea became known as the many worlds interpretation. In this view, every quantum event splits the universe into branches. When an electron passes through two slits, it goes through both, but in different versions of reality. When a photon strikes a detector, the universe divides, one where it hits, one where it misses. There is no special role for observers, no collapse, no cut between quantum and classical. The wave function continues, untouched, evolving smoothly according to Schrödinger's equation. Reality does not reduce its options, it multiplies them. The universe becomes a vast superposition of countless, ever-branching worlds. In this picture, we do not live in the universe. We live in one version of it, surrounded by infinite others, each as real as our own. In the many worlds interpretation, the universe does not select a single outcome when a quantum event occurs. Instead, it splits, branches, allowing all possible outcomes to unfold in parallel. Imagine flipping a coin. In one universe, it lands heads. In another, it lands tails. Both outcomes are real, and both give rise to their own future. The act of choosing does not erase alternatives, it creates them. This branching is not rare. It happens constantly, everywhere, all the time. Every time a photon reflects off a surface, every time an atom decays, every time a neuron fires, the universe branches. And because you are made of particles, you branch too. In one version of reality, you pick up the phone. In another, you let it ring. There is a version of you that turned left, and one that turned right, a life that unfolded, and another that could have. These are not copies in distant galaxies. They do not live elsewhere in space. They live in a different quantum branch, a separate, decohered version of reality that exists within the mathematics of the wave function itself. Level 3 is not a new place. It is a new unfolding of what already exists, embedded in the same quantum space as our own. At every moment, the universe is splitting, not into chaos, but into a vast, ordered structure of possibilities. Reality is no longer a single path, but an endlessly forking tree, growing outward with every quantum decision. And though you may only experience one branch, the others remain, evolving in parallel, forever inaccessible, yet forever real. The many worlds interpretation leads us to a haunting question. What happens to you when the universe branches? If every possible outcome truly occurs, then there is a version of you who wins the lottery, and one who loses everything. One who makes the phone call, and one who never does. But what if the stakes are much higher? What if it is a matter of life and death? Imagine this. You are handed a perfectly fair coin. If it lands heads, you live. If it lands tails, you die instantly. You flip the coin. It lands heads. Relief washes over you. You survive. But suppose you flip it again, and again. Eventually, the odds should catch up with you. Tails will come. Death is inevitable. But in the many worlds view, every outcome happens. Each time you flip the coin, the universe splits. In one branch, you die. In another, you live. From the perspective of an outside observer, your survival is just a matter of probability. But from your own point of view, something far stranger occurs. You never experience the branch in which you die. Your consciousness continues along the path where you are alive, no matter how improbable it becomes. This leads to the chilling idea known as quantum immortality. In every moment where death is a possibility, there exists at least one branch in which you survive. You, as a conscious observer, only ever follow those branches. In this way, your subjective experience never ends. Somewhere, somehow, you always make it through. But what is the cost of this survival? Does it mean there are infinite versions of you living in increasingly improbable worlds? Does your identity fracture across branches, no longer singular, but scattered? And what about those other yous, the ones who did not survive? Are they gone? Or are they just as real, just as valid, living out separate futures you can never access? Quantum immortality challenges our deepest assumptions about selfhood and mortality. It forces us to ask whether consciousness is tied to physical survival, or whether it is bound to the flow of probability itself. It raises questions that physics alone cannot answer, about the nature of experience, memory, and what it truly means to be you. In the Level 3 multiverse, you are no longer a single thread in the fabric of time. You are a cluster of branching paths, endlessly dividing. And while you may only remember one version, the others exist. Watching different sunsets, hearing different songs, making different choices. You are not just one life. You are every possible life that your quantum self could ever live. Not everyone has embraced the many worlds interpretation. To some, it seems excessive, wasteful even. Why multiply universes endlessly, simply to preserve the elegance of an equation? The Nobel Prize-winning physicist Gerard 't Hooft once remarked that it is a stupendous number of parallel worlds, which are only there because physicists could not decide which one is real. Others argue that if these worlds can never be observed or tested, then they belong more to philosophy than science. Hugh Everett himself received little recognition during his lifetime. After completing his PhD, he left physics entirely, working in defense and computing. He died in relative obscurity, unaware that decades later, his ideas would inspire a new generation of physicists and reshape the conversation around quantum reality. Today, the many worlds interpretation stands not as a fringe idea, but as one of several serious contenders in the ongoing quest to understand quantum mechanics. And it leaves us with a final, daring question. If Level 3 arises naturally from the mathematics of quantum theory, then what if all of reality is mathematics? For centuries, mathematics has been our most powerful tool for understanding the universe. From the orbits of planets to the structure of atoms, from the curvature of space-time to the quantum fields that govern the subatomic world, mathematics has not merely described reality, it has predicted it. Time and again, abstract equations written on chalkboards have uncovered truths no eye had ever seen. But what if mathematics does more than describe the universe? What if it is the universe? This is the bold idea proposed by physicist Max Tegmark. He suggests that the universe is not built on mathematics. It is a mathematical structure. Every particle, every force, every law of physics is simply a component in a vast, intricate mathematical object. And if that is true, then perhaps every mathematical structure, no matter how strange or abstract, exists in the same way ours does. Not in our physical reality, but in its own. This is the essence of the Level 4 multiverse. It is not a collection of universes separated by space, time, or quantum branching. It is a realm in which all possible mathematical realities exist. Each structure gives rise to its own universe, governed by its own internal logic, its own physical laws, its own dimensions, constants, and symmetries. Our universe is just one such structure, one among an infinite number, floating in a timeless sea of pure mathematics. In this view, reality is no longer defined by space and time, but by consistency and coherence. If a mathematical structure is internally logical, if its rules do not contradict themselves, then it exists. It does not require matter or energy. It does not need to be simulated or observed. Existence in the level 4 multiverse is a property of mathematical truth. This idea has curious parallels with the simulation hypothesis. If a universe is defined by rules and patterns, then perhaps it is like a program, executed by some higher system, running independently of our awareness. But Tegmark's proposal is even more radical. There is no computer, no simulation, no one running the code. There is only the structure. And if the structure exists mathematically, then it exists absolutely. You and everything you know are part of that structure, like a melody that exists because the notes fit together in harmony. Some physicists find this idea unsettling. It suggests that our universe is not special, not even among universes. It is just one logical possibility among uncountable others, a single equation among a library of infinite volumes. But others find it beautiful. In a level 4 multiverse, the mystery of why this universe dissolves. There is no why. There is only mathematics. Every universe that can exist does exist. It is a humbling vision. We began our journey staring into the sky, wondering what lies beyond the stars. We have passed through cosmic horizons, quantum branches, and eternal inflation. And now we arrive at a place where even reality itself dissolves into numbers and forms. If Max Tegmark is right, we are not just in the universe. We are the universe, written not in atoms, but in mathematics. Not observed into existence, but existing because the equations are consistent. And if that is true, then the final frontier is not out there. It is in the language of logic itself. The multiverse, in all its forms, has ignited one of the most spirited debates in modern physics. To some, it represents the natural conclusion of well-established theories, a logical extension of quantum mechanics, cosmology, and mathematical reasoning. To others, it is a philosophical dead end, a seductive idea that risks drifting beyond the bounds of science. As we journey deeper into these cosmic possibilities, we must also ask, where does exploration end and speculation begin? Supporters of the multiverse concept come from the frontiers of theoretical physics. Sean Carroll argues that the many worlds interpretation is the simplest explanation for quantum mechanics, one that removes the mysterious collapse and treats observers as part of the system. Andre Linde, one of the architects of inflation theory, believes that eternal inflation naturally leads to a multiverse of bubble universes, each with different physical properties. Max Tegmark pushes the idea even further, claiming that if mathematics can describe reality, then all mathematically possible structures exist. But not all physicists are convinced. Nobel laureate Gerard 't Hooft and others express deep skepticism. They argue that theories like the multiverse, especially levels 3 and 4, may be elegant, but elegance is not enough. A scientific theory must do more than explain. It must make predictions that can, in principle, be tested and potentially falsified. If a theory describes universes we can never interact with, is it still science, or does it become metaphysics? This question cuts to the heart of the philosophy of science. Karl Popper famously argued that falsifiability is what separates science from speculation. If no experiment can confirm or refute the existence of parallel worlds or distant bubble universes, then critics say these ideas should not be treated as scientific. They may be fascinating. They may even be true. But truth, in science, is not enough. It must be testable. Proponents respond by pointing out that science has always grappled with unobservable realms. Atoms, black holes, and even other galaxies were once beyond our reach. Quantum theory itself was born from mathematics before it could be tested. If a theory fits existing data, arises naturally from established physics, and offers a coherent explanation of otherwise puzzling facts, does it not deserve to be taken seriously, even if direct tests are not yet possible? Yet, the lack of experimental evidence remains a central concern. We have not observed a parallel universe. We cannot send probes into other bubbles. We cannot interact with alternate versions of ourselves in quantum branches. And while inflation, quantum theory, and mathematics are testable at certain scales, their multiversal implications often lie beyond our experimental horizon. This makes the debate more than scientific. It becomes philosophical. And perhaps that is what makes it so compelling. The multiverse pushes us to confront questions that lie at the intersection of physics and meaning. What is the role of observation? What does it mean for something to exist? Should the pursuit of understanding stop at what we can measure, or stretch toward the edge of what we can imagine? For now, the multiverse remains an open conversation. Not yet proven, not yet disproven, suspended between mathematics and mystery. The multiverse remains beyond our reach, for now. But physicists are not standing still. Some researchers are searching for signs of cosmic collisions, subtle scars left on the cosmic microwave background, the oldest light in the universe. If our bubble once brushed against another, it might have left behind a faint imprint, a fingerprint from another world hidden in the static of the sky. Others look further ahead. Could wormholes, if they exist, provide a passage between universes? Could future technologies detect signals leaking from higher dimensional space? Theoretical physics is evolving, with new frameworks like string theory, quantum gravity, and holographic duality pushing us toward deeper questions. We may not yet know how to test the multiverse, but every step forward in fundamental physics brings us closer to the edge, where imagination meets evidence. From Edward Quinn's Fading Clouds to the endless branches of the multiverse, we have followed the arc of human curiosity, from maps of continents to maps of reality itself. But is this the end of the journey, or merely the beginning? The multiverse invites us to think beyond the visible, to embrace the unknown not with fear, but with wonder. Whether these other worlds exist or not, the pursuit itself reminds us of who we are, a species of dreamers, of explorers, of scientists. And in the silence between the stars, it is imagination that lights the way forward. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.